Oh. Shit.
All right, I see it.
Yeah, one more. Can you plug this into your laptop, I think?
For what?
For the slides. Can you go on that?
Yeah.
This actually makes a little...
I need the document. Hold on.
That way I can still use my software.
Sure. Wait, so are the slides also going to be on the stream?
Yeah, they're going to be on the stream as normal.
So you're going to be advancing the slides on your laptop like at the same time?
Yeah, probably, or somewhat at the same time. I'll be here. I won't mind going anyway.
So I'm seeing this. That looks bad. I can't really. I don't know if that's what it looks like on the live page.
That's really weird. Video, 30 frames per second, 480. I'll push again. So let's see. There it is. It's stable now. Okay. Let's see what actually. Yeah, somewhat manageable. Oops.
Okay. Are you guys on your side?
I'm going to go back to slide one. Lights.
Testing. Wow, that's super loud. I have like a loud voice already. This is a little intense. Okay. Hey guys, thank you guys so much for coming, guys and girls, and thank you for your patience. We've had some technical difficulties, but I think we're all good now. We are streaming this event on YouTube as well. I tweeted it, so if you guys want to share that with your friends, you can look at twitter.com/lrettig, L-R-E-T-T-I-G, and you'll see a YouTube link there. So thank you to, what's that? Yeah, oh yeah, okay, cool. I'm Lane, I'm a member of the Ewasm team. You're going to hear a ton about Ewasm tonight. But yeah, why don't you tell us a bit about Starfish?
Give it up for Lane for putting this whole thing together. This is going to be very fun. My name is Matt, I'm the co-founder of Leasers over here. We put together Starfish Mission about 6 months ago. Originally the idea was blockchain co-working space that's kind of morphed into blockchain community space. So we do a ton of events. We have office space. We just hooked up a new member package where you can work out of the space 4 days out of the month for $99 a month. And if you don't use those, then they can roll over to the next month. So if you find yourself in San Francisco from time to time and need a place to work, and maybe you're not all that sold on WeWork, please let us know. We've got cards over here on this table. I just want to welcome everybody in from out of town. Welcome to San Francisco. Enjoy Blockchain Week, and yeah, give it up for Lane and the rest of the Ewasm team. It's going to be a great event.
Thank you, Matt. I run a blockchain co-working space in New York for Crypto NYC, so I know how hard it is to do what you guys do. So again, thank you. It's just really awesome to be part of this community, and also thank you to everyone who's organizing San Francisco Blockchain Week. I don't know if it started yet. Is this it?
This is it.
Is this
We're
it?
here. We're
All
here.
right.
This is it.
So we're officially kicking off San Francisco Blockchain Week, so thank you guys for coming. Yeah, we've got a real star-studded cast of folks to come speak tonight. You're going to hear some really interesting talks from members of the Ewasm team. We have a special guest as well that we might see later. So we'll we're gonna do 3 short talks. The first one is going to be an introduction to WebAssembly and to Ewasm. That's Alex Berzazzi. So Alex is actually the lead of the Ewasm team. So really privileged to be able to hear from Alex tonight. Then you're going to hear from Jake Lane over there, who's going to do a talk on, what did you talk on, Jake? Precompiles, so that's super deep technical stuff. And then I'll come at the end and do another talk. And we may have time for a panel at the end. Am I missing anything? Yeah. Cool. Sorry? Oh yeah, okay, right, sorry, there's one other thing. So we've been very heads down for the past few months building this new technology, and this is sort of our first time. This is our first time unveiling it to anyone in person, so it's very exciting. We're all a bit nervous. We did a little bit of a demo on our community calls. We do these community calls every 2 to 3 weeks. That was the very first time we showed our testnet. So we've been building this testnet. We're going to try to do a live demo. We all know how hard live demos can be. I guess after your talk, Alex, is that the plan? And yeah, I mean, we are officially launching Ewasm and its testnet at DevCon in about a month. And so this is, you guys are getting a sneak peek of stuff that no one else in the world has seen. So we're super excited. Hi, Internet. All right, Alex, take it away. I'm going to finish this slide for you.
Okay. Is it loud enough? Cool. Okay, I guess a few questions up front. Raise your hands if you know what Ethereum is. Is somebody not raising his hands? Raise your hands if you know what EVM is. If you wrote a Solidity contract. Have you heard about WebAssembly before? Did you write anything in WebAssembly? Oh, a couple of people. Have you heard about the Ewasm before this? Are you excited for Ewasm? Okay, so you have the clicker, or how does it work?
You ready?
Yeah. So this is just going to be an intro. That's my name, and that's my GitHub username. You can look it up and find a lot of things we do as a team. Then you want to click, or... Okay, so let's just start with a couple of issues we think the EVM has, and I just need to look there because there's a lot of things there. So basically it's just not really designed for performance. And it has some weird features. So first of all, it mixes two different things into the same instruction set. It has computational instructions, and it has instructions which would be way more high level. So some of those would be anything querying the state, interacting with the Ethereum state, interacting with other contracts. And my personal favorite one is SHA-3. So why is SHA-3 an instruction? It's way more higher level than it should be. And lastly, there's not too many languages for EVM. There's only really Solidity and Viper. Anybody here wrote a contract in Serpent or Viper? Nobody. Have you heard about LLL? Oh, a couple of people. But still, nobody has written anything in that, right? Have you heard about Flint? Nobody. So it's really only just Solidity as the sole language for the EVM. So that's where we started. And now have a look at the clicker.
Sorry.
Okay, so WebAssembly, many of you have heard of WebAssembly before. Just a couple of notes. It's designed by a W3C working group, which means all the big companies such as Mozilla, Google, Apple are behind it and have dedicated engineers to it. And as a result, it's supported by all the browsers, which is really exciting, but we're not working on the browsers. The main difference between the design goals of the EVM and WebAssembly is WebAssembly is designed as a generic purpose instruction set. And it is designed to be much closer to a regular computer. The EVM wasn't designed for that. As a result, we really hope that it's going to give certain benefits. So one of those is going to be probably a speed up, because whatever bytecode exists in WebAssembly can be translated much more closely to machine code. But it is also designed to be much more extensible. Even though we have this understanding that the EVM is tiny and it's controlled by a smaller set of people, and as a result, it will be much more easier to change it, improve it, update it. But in the past 2 years, we haven't really seen that process to be quick. So we kind of hope that with WebAssembly, because it was designed with extensibility in mind, it's going to be much more quicker to extend if any devices. Yeah, I guess, can you click this? Just a quick overview. There are a ton of languages already supported by WebAssembly, or rather, a ton of languages can be compiled to WebAssembly. I just want to mention a couple of those. Rust is the one which has the best support. So a lot of things in the space, especially in the blockchain space, are being written in Rust, because that has the best support for compiling to WebAssembly. And as a result, a lot of things we write is written in Rust. Another interesting one is assembly script. Have you guys heard of TypeScript before? So TypeScript is a typed version of JavaScript, if you put it that way. It kind of looks like JavaScript, but it has types. And assembly script is a version of TypeScript, or something which looks like TypeScript, which can be compiled to WebAssembly. The interesting part with assembly script is it's done by a small team, and they're really rapid in implementing changes and improving the language. And we actually work closely with them to create Ewasm support in assembly script. Yeah, I mean, there's so many languages which already support it, but we only focus on a couple of them. An interesting one, why is Yule and Viper on the list? Have you heard of Yule before? But you heard of Solidity. So Yule is a language used by the Solidity team where we take Solidity input, we translate it to Yule, and eventually we translate that to EVM bytecode or Ewasm. So I say this in present, but this isn't actually true right now. So this is the goal we have for the next year, to have this pipeline, and as a result, Solidity will be capable of compiling to WebAssembly. And the last part I wanted to mention there is the K framework, which is an outlier. Have anybody heard of the K framework before? So K framework is, yeah, it's hard to put it, but you could say it's a formal verification compiler framework where you can specify syntax and semantics of languages, and it has a lot of different features, but essentially you can execute these languages or even translate between them. The K framework has support, maybe not full support, but it has limited support for WebAssembly. And we actually work closely with one of the main developers behind the K framework to implement Ewasm support. You want to move on? So the main question now is what is the main goal of Ewasm and why do we do this? So our main goals with Ewasm is to improve the execution engine of the Ethereum network. And the main goals in that is we want to have an extensible platform. We don't want to have a platform which cannot be easily changed, cannot be improved, and doesn't have a lot of people behind it. When we started to work on Ewasm, which was 2 years ago, we did a review of all the different instruction sets out there. For example, we looked at Java, we looked at CLR, which is .NET, and RISC-V or RISC-V, I don't know how to pronounce that. But we looked at all the possible options, and out of these, WebAssembly seemed to be the best option. The main benefits you're going to get with WebAssembly is there's so many different people and companies behind it, and so many languages behind it, that hopefully a lot more tools and a lot more languages will be made for WebAssembly. And the main one I would like to emphasize here is the analyzers and the optimizers and the debuggers. So analyzers here mean any kind of tools which can be used on WebAssembly bytecode or languages supported by WebAssembly to analyze those for security vulnerabilities or any kind of problems. The EVM ecosystem or the Solidity ecosystem has a limited set of tools doing that. Sorry. But more mature languages such as Rust or C would have a much wider tool chain to do that. So that's one of the main benefits we hope to get is tapping into this much bigger space of tools and security tools, especially for WebAssembly. And of course, we would like to improve some of the shortcomings we have with EVM. So I don't want to go too deep into what Ewasm is, but to put it shortly, we didn't really change anything in WebAssembly. So that's the beauty of it. We didn't need to change anything. We just use whatever solutions WebAssembly offers to extend it, and we extended it. So in practice, what that means is you can use functions exposed by the Ethereum node, and you can use that from any language which compiles to WebAssembly. So as an example, let's say if you see us take a C code and you would use a standard library in C, you could do practically the same thing when writing the contract. And those calls into the standard library will translate into calls into the Ethereum client. Obviously, this isn't the C standard library, this is an Ewasm specific standard library. But there's no need to modify a compiler, but there's no need to modify anything deep. It is just a framework supplied by us. Yeah, practically, that's all which needs to be said. Lynn? So where do we stand right now? We do have a quite stable API, which hasn't really changed in the last couple of months. And therefore, it's really there to be discussed by a wider audience. However, we do expect changes to happen in that API. So it's not set into stone. But it's quite stable already to be used in a testnet setup. Regarding the testnet and the clients, we have currently native support for 2 different clients already. PP Ethereum, which has been recently rebranded to Aleph. I'm not sure if anybody heard about it. It's not really used by the mainstream, but it is very much used for test generation in the Ethereum network. So it's a very important piece of client out there. And that has support for Ewasm. But the other one which probably everyone has heard about is Go Ethereum. We do have native support in Go Ethereum. Now there's an interesting part there. We do have universal support. So what that means is there's this tiny remark EVMC. So we're not going to really talk about EVMC, but EVMC is just an API. And if you happen to be an Ethereum client developer, all you need to do is support the EVMC API, take our Ewasm engine, to which you can communicate through this API, and you have Ewasm support. There's nothing else which needs to be done. Well, we do have like 3 languages listed there, but 2 languages we actually focus on is Rust and AssemblyScript. Rust is our main focus for system-level contracts, which are like contracts which do system-level things. So anything which would be part of the consensus model, or anything which would be a commonly used helper library. While the focus for AssemblyScript would be for any kind of contract user would write. But if you happen to be fluent in Rust, you can already write contracts in Rust also. So we're going to touch on this Precompiles and system contracts bit. Jake's going to talk much more about that. We have all of these. Are you familiar with the Precompiles in Ethereum? Somebody raise? Anybody? A single person. So basically, Precompiles are a way to fix a shortcoming in the Ethereum network. As you know, in Ethereum, every kind of execution is measured in gas. And the main purpose of this measurement is to limit the time that the execution takes. And as it turned out, a lot of things which would be fairly commonly needed, such as hashing methods or recovering a public key used in a signature, all of these, if implemented using EVM instructions, would take so long, would take so much gas, that you wouldn't be able to run it in a single block. So therefore, these Precompiles came along, which are practically subsidized implementation of common contracts. And every single client today has to implement that in their native language. And what we have done here is we have replaced that, and we supply a single implementation of all of these Precompiles, of which there are today, I think, 8 or 9. So we supply an implementation of these in WebAssembly, and the clients don't need to implement it one by one. This is actually a really interesting topic, but yeah, I think Jake can talk way more about that. The the main two focus points we have right now is looking to interoperability with more blockchains, because a couple of other blockchain projects are also exploring the use of WebAssembly. And it would be cool if there would be a standard base between these, and there would be more ways to move contracts across these different systems. So that's one of the focus points. But the more important one where we actually have made progress is research into JITs and ahead-of-time compilers. I'm not sure, are you guys familiar with JITs or anything like that? So just a quick note, basically when you have any kind of bytecode, maybe the EVM or WebAssembly, there are a couple of ways you can execute that. A very simple way to do that is you execute instructions one by one, which is fairly slow. It shouldn't be that slow, but the EVM has these weird design decisions which make it even more slow than it's supposed to be. And you can do the very same thing with WebAssembly. You can execute it line by line. But you can also take a more advanced technique where you take the bytecode, translate all of that to your machine code, and you just execute the machine code. So that would be ahead-of-time compilation. But there's an even more complicated way, which is called JIT, which stands for just-in-time compilation. And what it does is it first does this line-by-line execution, but if it finds that certain parts of the code are used again and again, they're used regularly, then it will compile those to machine code because it's used frequently. All of this sounds really great, but there's an issue with this. Can you guess what could be the issue with this? Yeah, I don't want to be too hard, but it's quite funny. So basically, when you execute a contract, you want to have this gas cost accurately, somewhat accurately defined so that no client in any circumstances would spend more time than they should. They may spend less time, but they shouldn't spend more time on executing any given piece of code. The main problem with JITs is that in many cases it is possible to craft a certain piece of code which may not be useful, it doesn't really matter, but it is possible to craft a certain piece of code which will blow up this compilation process. And what that means, where it should take, say, 10 milliseconds, I guess, microseconds. Anyway, it shouldn't take too long to do this compilation. But if you generate this weird set of code, you can blow it up 10x, 100x, 1000x. And what it eventually means is that you're going to make a denial of service attack on the network. So this is quite an important thing to research. So that's our main focus point right now. I see all of you are really excited to participate in this, and there are a lot of different ways to do that. So you don't actually have to write code. There's no need for that. The first thing you could do is just listen and ask questions, because we need to get better at explaining all of this, documenting all of this. So the first thing you should do, ask questions. And then you could also help us write documentation. That's no code, just documentation. But if you want to write code, you're welcome. So please, actually, let me if you want to go.
Where am I going? Just next one.
Okay, so the first one, github.com/Ewasm is our main repository. And there is another that's the organization. So there's a repository below that called design. That contains most of the documentation. So that probably is a good way to start. But I can tell you it's not the best written documentation. So you're going to have a lot of questions. So please ask those questions either in the design repo or just join the particular channel. And no question is bad. Everything is great. Please ask questions. We also do bi-weekly, more like, every now and then calls with the community, which anybody can join. It is usually recorded, put on YouTube, and usually either we use Zoom or Google Hangouts. People can join, ask questions. It lasts usually for an hour, and that's another great way to interact with us. I think that's it. Thank you. Do we have any questions right now? Do we have an next mic? So we do plan to have kind of a panel. So maybe another option, ask a few questions now. We go through the other two talks, and then we can dive into way more questions. Yeah, maybe like 3 questions.
Have you tried, how far have you gotten with the JIT? Is it actually, have you tried to figure out how useful it would be? It feels like most code is all around like once, or we do cache results between like blocks, and every block like needs to cache on proteins.
It's actually,
Yeah, that's a good question. We have, so first of all, even though you didn't ask that, but when I thought that there's a way to find these bugs where the JIT would blow up, and we actually managed to find at least I think 2 of those occurrences. So the problem does exist. And then regard to your question whether we would cache execution across blocks, we have a couple of different ideas what would really make sense. First of all of these precompiles frequently use contracts, but it's really up to the client to do all of that and decide. And our goal is to make these decisions really up to the client, so we have to set certain things in a way that they are flexible enough to make those decisions. So we don't really have a full answer whether it makes sense to cache contracts across blocks. But that would be quite easy to tell if somebody goes to the blockchain and looks up the links between different blocks. But we haven't done that yet.
This is what's
that's
showing
a
on the
good
screen
idea.
right now.
Thank you.
It is working. Have you changed?
Yeah, I might have missed it before, but I was wondering if you guys have any benchmarks, either efficiency benchmarks, speed, what I do, for Ewasm compared to the existing Ethereum virtual machine.
Oh,
that's a great question. And we actually do have some benchmarks.
It's called Ethereum Foundation.
We have made a couple of benchmarks last year for DEF CON. You could look up Greg Colvin's talk at last DEF CON, which has a couple of the benchmarks there. But also, right now, one of the main focus points we have is doing these benchmarks. So right now, there's like a team of 3 people within the team working on benchmarks. I think some initial numbers.
Like, how do I?
Yeah, I don't think I have numbers comparing them to EVM, because there are 2 parts of the benchmarks we're doing. One benchmark is comparing something against the EVM, so comparing a WebAssembly engine and a contract on the WebAssembly engine against the same contract on EVM. That's one of the benchmarks you have to do. And the other benchmark is comparing different WebAssembly engines, using the same contract on different WebAssembly engines. And there is a big difference between the WebAssembly engines regarding performance, which we hope to share at DEF CON, but I don't have numbers to share yet. One last question.
I wonder what major bottlenecks you guys face during Ewasm development.
Okay, it is working now. Yeah, it's live.
It's funny enough.
By the way, this is
I think one of the major bottlenecks we have there is writing test cases. Because nobody ever wants to write test cases, even though it's one of the most important things to do. Luckily, we have overcome the challenge, and we have really good test coverage of all of these features. But I think that was the major hurdle we had, writing test cases. People don't like to do that. Thank you.
Thanks, Alex. All right, I'm going to pull up the next slide. Jake, are you ready? All right, guys, this is Jake. Jake is super smart, and he's going to talk to you guys about Ewasm Precompiles. Alex introduced the topic a moment ago, and yeah, if you're curious what they are, or why they matter, or why they're exciting to Ewasm, you're Is the stream ready or do you need a moment? You good?
Hello, everyone. I'm Jake, as Lane already said. I work primarily on Hero, which is the Ewasm virtual machine implementation, and various other Ewasm toolchain projects. But anyway, I'm going to be talking right now briefly about one potential route to introducing WebAssembly on the mainnet that the Ewasm team is exploring, and that is that's Ewasm precompiles. So, using Ewasm as a common medium for executing precompiles on a chain has a variety of benefits, including streamlining the process of developing and introducing new precompiles on the mainnet safely and efficiently. Next slide.
Working on it, sorry. I have too many things open here. There we go. Perfect, sorry.
All right, so as you guys, by show of hands, demonstrated earlier, most of you have some experience with Solidity and hence do have at least a rudimentary understanding of what precompiles are and how they work today. But if you don't, I'll be going over them briefly right now. So precompiles today are essentially special contracts that are used on the main chain for computation that cannot efficiently be handled by EVM1. Now, next slide. Okay, so among these types of problems that the EVM is not suited to, we have cryptographic primitives, one-way hash functions, pairing-based cryptography. Next slide. And, well, over elliptic curves, for example, we have BN128 curve operations existing as native precompiles right now on the main chain after Xantium. And also just generally useful things like, for example, the identity function, which, although it's kind of hacky to have such a simple function as a precompile, it sometimes is useful for cheaply copying data. We have modular exponentiation, which is also used in cryptographic primitives, and we have ECD SA signature recovery, which is used for driving the address from a public key. So, well, precompiles by definition are precompiled. They're implemented natively by each client, and they're deployed via hard fork because they have reserved addresses that require that can't be created using the standard contact deployment method. So I'm going to be giving you a brief MS Paint style kind of demonstration of why the existing system for deploying precompiles is somewhat flawed. So here we have Bob, who writes an EIP because he wants a precompile to be deployed for his favorite type of non-EVM suitable computation. And so here we have a super smart, core dev saying, yes, you could do that. You go ahead and if you have it fully spec'd out, and we'll include it, on the next hard fork. All right, so Bob and his friends from different client teams go on to implement the precompile on their respective clients. And, well, because of implementation-specific behavior, where you essentially have, consensus bugs resulting from the fact that people were writing in different languages for possibly different native targets that somewhere along the line introduced behavior that is not directly in line with the specification for the precompile. So Ewasm promises to streamline this process by the sole virtue of having the precompile implementation be pretty much the same across each client. So for this to happen, we need all clients to maintain a WebAssembly execution engine, preferably a JIT, because as mentioned before, we can use JIT compiler to reach very close to native speed, and with a restricted subset of WebAssembly, we can also worry less about the denial of service vectors that were previously described. Okay, so, well, when we have this, we can essentially have the implementation of a precompile be the same in bytecode across all clients. And that means that all of the implementation-specific behavior, assuming that the same precompiled bytecode is running on all clients, all of that behavior, it implies that there would be instead above in the execution engine. So in the long run, it's much easier to maintain an execution engine and keep in line with a single spec than have to do the same process for every single precompile that has to be introduced on the chain. So now, in the case of the bytecode, you're more focused on making sure that it's in line with the specification for the precompile rather than in line with the other implementations of the precompile for other clients that may or may not be wrong or right. Sorry. So, well, I just talked a lot about what we could change, and so what will essentially stay the same about precompiles, especially in a post-native precompile world. So, well, first of all, we're not going to trash all the existing ones because they're pretty good, they do the job, and there's no point just throwing out that work and trying to radically redesign it. And the next one is, well, precompile, well, by nature will still be deployed by hard fork rather than through a more user-oriented process like sending a create transaction, because we need to reserve addresses. So there's also a potential idea to introduce a different class of contract that has some of the performance guarantees and a more precompile-like set of restrictions that will make it easier for users to deploy higher performance contracts on the chain. But for now, that's kind of that's out of scope of the proposal right now. But yeah, this has been Ewasm Precompiles. Thanks for listening, guys. Yeah, do you guys have any questions? All right, cool.
How do you guys feel? We have another kind of 15-minute presentation and then probably a panel chat. Do you guys want like a 5-minute break now, or do you want to keep going? Just shout if you have an opinion. Keep going. Anyone over my dead body? Anyone really need a break? Okay, so we'll do one more quick talk and then a quick break and then we'll do the panel. Jake, can you help me with the slides on the other one? The slides need to be manually. Maybe a little bit of they're separate, so you could just advance that one. I'll do this one. I'll do this one. If you could just do that one. And then so. I'll do the screen one. Yeah, so the slide, there's just too many slides here. It's just going to be rapid fire, so it's not going to work super well if I have to say every time. Anybody? Are we good? Cool. This, and I guess we'll put out the camera as well. I'll do my best to stay in the frame. This talk is kind of experimental, so bear with me. This is not like, this is a little bit out there, and this is just kind of exploratory. And I kind of intend this talk as a bit of a conversation starter, so I hope that you guys do have questions. And feel free to just jump in anytime. I'm going to attempt to do like a super whirlwind overview of like past, present, and future of kind of the overall compute stack. So a little bit ambitious. And yeah, and also, as I said, we're going to do this kind of panel thing after this is over, after a short break, so we can also dive deeper into some of this stuff now. So who knows what these are? What is this? Someone tell me. Bunch cards. Yay. All right, so slightly before my time. So yeah, so when way back, circa kind of 1950, when people were programming computers, this is kind of what it looked like. And you were basically writing machine code instructions directly into these punch cards and feeding them into machines. And so the stack, so actually I was informed that assembly wasn't even a thing at this point. It was basically just machine code, which kind of sucked. And programmers did this for a while and then said, hey, this is kind of painful, so let's build some tools on top of that that are kind of macros or shortcuts that make it easier to write programs. And that's kind of where assembly came from. The next thing that happened was people said, hey, we have these tools, we have these macros, we can write more complicated programs, so let's write better operating systems. And so you now have an operating system that's written in assembly that sort of compiles to machine code that's running on a CPU. Right? So we're still kind of early computing here. The next kind of era of computing was the mainframe. So maybe the punch cards have gone away, right? And we have kind of people writing like typing programs on keyboards. So what do we have now? Well, we have an operating system that's written in a programming language with probably some assembly components to it that compiles to machine code and is running on hardware. And as you can see, the screen's a bit full, so I'm just going to kind of collapse the stack and keep moving. So we're just going to call this collectively the operating system. We all know that an operating system, as I said, is written in some programming language or collection of languages and compiled to machine code running on a CPU. And the next thing that happens, this is again super whirlwind, and I know I'm skipping a lot of steps, is that we get interpreted languages. So now we have languages, the modern versions being things like Perl or Python, that are running inside an interpreter, which are a script, which is running inside an interpreter, which is written in a programming language, which compiles to machine code, which is running on an operating system on hardware. We're kind of, jumping forward here. And that's more or less kind of the state of computing in the 1990s. There wasn't a whole lot of other stuff. So this is, let's say, circa 1995. So what else can happen here? So the next kind of big evolution of computing was virtual machines. And so this concept of a hypervisor, which is a piece of software that allows you to actually run an operating system inside of it, kind of emerged in the, I guess, mid to late 90s. And a hypervisor is a piece of software that is written in a programming language that is compiled to machine code running in an operating system running on hardware. You can see things are beginning to pile up and get more interesting. So here's where, okay, so this is the first kind of like black magic thing that happened. Now we have this nice little recursion thing going on here. We now have an operating system running inside a hypervisor that compiles the machine code that's running inside a low-level operating system that's running on hardware. And again, we're collapsing the stack. So now we have, what can we do inside this virtual operating system? Well, we can do anything, right, that we did before. Right? So let's, for example, write a script. Let's say we have a Python script that's running in a Python interpreter that compiles to bytecode. And there's a distinction between bytecode and machine code I learned today. Right? That is running inside this operating system, which is a virtual machine that's running in a hypervisor, which is running on a real machine. And it turns out that we can actually run multiple virtual machines on a single physical machine. And so if we kind of introduce another abstraction here, these are what we refer to today as VMs, or virtual machines. And this is a super, super, super common technology today. We can run many virtual machines on a single machine. And if we abstract slightly further, are you keeping up? This is like super fast, thank you. It's not just VMs, right? We can do other interesting things like containerization. So this is San Francisco. I'm assuming you guys all know what Docker is and what containers are and what they do. And so it's not just hypervisors. We have very complex, interesting process isolation support built into kernels now. And so you can have apps running in containers, which, if you zoom out, are a lot like virtual machines, and we can have virtual machines all running on top of an operating system to deal with it. And that gets us to, more or less the present, right? So we have these server farms. Each of these is probably a rack that probably has 10 or 20 physical computers in it, and each of those probably has, I don't know, 2, 6, 8, some number of VMs running on it. And these things basically run the centralized computing infrastructure of the world today. What else can we do with an operating system? Well, we can run a web browser. So a web browser is a piece of software. It's written in a programming language, something like C. It's compiled in machine code that's running on an operating system. And once we have a browser, we can do some interesting things, like introduce this display layer, right? So we have things like HTML, CSS, web pages that are displayed in the browser. It's compiled to the machine code that's running on the operating system on the hardware. And we can also introduce JavaScript. So we're just beginning our forwarding into the modern web right now. So JavaScript runs inside this thing called a runtime, sort of otherwise known as a JavaScript engine. There's a slight distinction there, but basically it runs inside this thing, which is sort of like a virtual machine inside a browser, inside an operating system. And the display piece is not particularly relevant to this talk, so I'm going to drop that. And what can we do with JavaScript? Well, we can build a web page like this. This is basic HTML, CSS, maybe some JavaScript. So this brings us up to late 90s, early 2000s. So we're collapsing again. What else can we do with JavaScript? Well, the next thing that happened is these JavaScript frameworks emerged. So this is the things like jQuery and React and Angular and Vue that we all know and love. Very few people, basically nobody writes vanilla JavaScript because you can leverage and just write much better code with frameworks. So that's running on JavaScript in the JavaScript runtime inside the browser, which is running on the operating system on the hardware. And finally, we can build an app. Okay, so I've lost track of how many layers in the stack we have here. But this is a modern tech stack, a modern front-end technology stack. And we can run, of course, multiple applications with JavaScript in the JavaScript runtime, in the browser, on the operating system, on the hardware. And as I said, this brings us to the modern web application, which could be running on desktop, it could be mobile, it could be anything. So these are the apps that we interact with every day. This is a tangent, but web apps in some sense are kind of taking over the world. A lot of the things that we consider desktop apps are in fact web apps that are packaged in something like Electron. So if you're running Slack, if you're running Spotify, a lot of popular apps like that are actually web apps. And again, the same tech stack. Okay, so now this WebAssembly thing has emerged. So Alex introduced you guys to it before, and the WebAssembly 1.0 standard was just finalized last year. So it's really, really, really new. As Alex said, it has the backing of some really legitimate companies, not just a bunch of crazy blockchain hippies like us, but it has Microsoft, it has Apple, it has Firefox. A lot of companies are part of the working group that are pushing this technology forward. So it's a real thing. Like Ethereum is kind of a thing, we're getting there, but like this is a real thing. Like this is something you can like talk to your colleagues and your parents about, and they won't laugh at you. And I just want to emphasize, like that's why one of the reasons I'm so excited about adding Ewasm and adding Wasm to Ethereum, because we are adopting real-world technology that's battle-tested and being used in production environments all over the world. So, where does Wasm fit in? Well, you can argue whether it belongs on top of the JS or next to the JS or below the JS in the stack, but I don't want to get too bogged down in the deep technology details here. For the sake of this talk, let's just assume that Wasm is running on top of JavaScript, which is, so it's controlled by JavaScript, right? What that means is that the JavaScript, a JavaScript application can load and control a Ewasm module or Ewasm application inside the browser. So inside the JavaScript runtime, inside the browser, compile the machine code, running on the operating system on the hardware. And what can we do with Ewasm? Well, everything that runs Ewasm is compiled to Ewasm bytecode. So what can we compile to Ewasm bytecode? Someone give me an answer. What can we run on Ewasm? Anything. Pretty much anything, in theory. Obviously, there's some missing features, like there's no garbage collection yet, there's no threads, but there will be. So any application written in a programming language that can target LLVM, and part of the LLVM pipeline can target Ewasm. That's a pretty exciting development. So we have apps. We can write any type of app we want. Anything. So I'll just pause for a sec, like just ponder the implications of this for one moment, right? You can run anything at near native speed, at something like 90% native speed inside a web browser. I mean, this changes everything. I really do feel that way. That's why I personally think Ewasm is such an exciting technology. One fun thing we can do is we can kind of run an operating system inside a browser. Maybe not a full operating system, maybe just kind of a shim thing or like an emulator or something. What are operating systems written in? C, mostly, and C compiles to Ewasm. So let's shrink the stack a bit more and add some more on top. So in theory, what are browsers written in? C-ish, C++, whatever. So you could, in theory, pick a browser, which is written in a programming language, compile it down, so it'll be talking to an operating system, or thinking it's talking to an operating system, which is all compiled into Ewasm bytecode, which is all running inside Ewasm in the JavaScript runtime in a browser, which is running on an operating system on some hardware. And the possibilities are kind of endless, right? I mean, there's a nice recursion here. We have a loop, right? So in theory, you can keep piling things on. I mean, eventually, the whole thing will come to a screeching halt, but the tech's getting better and getting faster. So this is kind of the turtles all the way down moment. Just pause to appreciate how important a moment in the history of computing this is. We've achieved like this beautiful recursive, I don't know, symmetry. And this is my favorite example of this. So this is an app. So this app is called the GIMP, which you might be familiar with, which is an open source image manipulation application, which is basically a pile of C and C++, which here is compiled down to Ewasm bytecode, and it's running inside Chrome. And what is Chrome written in? Well, C or C++, it's just a bunch of C. So Chrome is compiled down to Ewasm running inside Firefox, which of course is compiled down to bytecode or machine code running on an actual operating system. And if you zoom in, if you have a keen eye, you'll notice that like the Chrome controls here are like Mac controls, and the Firefox controls are like Windows controls. And so this is actually what's going on here. So we have GIMP running inside a Windows emulator, running inside X Windows, which is C or C++, compiled to Ewasm, running inside Chrome with the Precompiles an open source version of Cocoa. So it's like a Mac emulator, which again is a pile of C, which is compiled to Ewasm, which is running inside Firefox. And again, it's turtled all the way down. So it's a pretty big stack. This particular example is not mine. This comes from a gentleman named Gary Bernhardt in a talk that he gave at PyCon in 2014. So super visionary. This was 4 years ago. This is before Ewasm even existed. So he was talking about ASM and Ewasm.js, if you know what that is, the precursor to Ewasm. This talk is fantastic. It's super inspirational. It's the inspiration for what I'm talking about here, and I highly recommend looking it up. Just Google the first inventor of JavaScript. He's a far better presenter than I'll ever be. So people asked me recently, why am I working on Ewasm? Why is that the most interesting part of the theory of a blockchain? And when I thought about it, I realized it was actually this talk that inspired me to work on it. Cool. So we haven't talked about Ethereum yet. So let's talk a little bit about Ethereum and how Ethereum fits in. So what is Ethereum? It's an app, right? Written in C or C++ or Go or Rust or one of these other languages, which is compiled with machine code, which is running on the operating system on hardware. And Ethereum today in production has this virtual machine called EVM. Right, so what can we do with EVM? Well, we can run smart contracts on it, written in something like Solidity. I should have inserted EVM bytecode, right? So the smart contract is written in Solidity or Viper, compiled to EVM bytecode, running on the Ethereum virtual machine inside the Ethereum client, which is compiled to machine code, which is running on an operating system on a CPU. Another thing we can do is we can add frameworks. So this is early days for Ethereum. These are beginning to emerge, but there's things like ZeppelinOS, which kind of wrap an application and it consists of kind of trusted code. So this really resembles like the JavaScript frameworks, I think, and we'll see a lot more of these emerge. Enter Ewasm. So how does Ewasm change the picture? You've heard from Jake and Alex today a bit about Ewasm, so let's explore how it fits into the stack. So instead of EVM, we now have a Ewasm interpreter inside Ethereum. Anybody want to guess where we're going next? Let's keep going. So, with WebAssembly, with the WebAssembly interpreter, we can run any WebAssembly bytecode, right? Compile once, run anywhere. So we could take a framework like ZeppelinOS and a smart contract, and we could run them through, through Ewasm interpreter, so Ewasm compiler or interpreter, running on Ethereum, compiled to machine code running on an OS and CPU. So we've got this Ethereum stack happening, but we can do other things with this computer. So what if we just run a Ewasm interpreter outside of Ethereum? And there's several of these. So a common misperception about WebAssembly is because it has web in the name, that it only runs in a web browser, or it's sort of exclusively designed for a web browser. That's actually very much not the case. It's a much more powerful virtual machine, and there's several independent open source tool chains that can be used to run WebAssembly code, run that VM on any operating system. It's really performant. It's a bit like Node, like the difference between running JavaScript on the front end versus the back end, if you're familiar with that. And the exciting thing is that we already have Ewasm support on a whole host of devices from all major browsers. It can be run on any device that supports JavaScript. Pretty much any device in the world. We're talking toaster ovens and satellites and connected devices. So we can run Ewasm bytecode directly, not in Ethereum, and so we can run an app, any Ewasm app, directly on our operating system outside the browser. So, is there any parallels that are beginning to appear here between these two stacks? If we kind of slide this up a little bit, okay, right, we've got something compiled to Ewasm running on an Ethereum node, we've got something compiled to Ewasm that's just running directly on the computer. What are smart contracts? They're just apps. And I don't love the word smart contracts. I think as we try to take Ethereum mainstream, we need to begin using a language that the rest of the world is used to, right? Going back to my point earlier, things that we can talk to our parents and our colleagues about and they won't laugh at us. So I don't even like the word app. I just think they're just apps at the end of the day. But apps with specific characteristics, specific performance considerations, and security considerations. They're just apps. Again, pretty parallel, right? So this is the hocus pocus. So just pay attention to this part. So what if, see if I have a slide over right here, right? What if we do this? This is the question I have. And this is where I've just stepped off the deep end. We're now in pure hypothetical territory here. And as I said, I don't claim to have this all figured out. This is just exploratory. But it's the type of research that we're doing and thinking a lot about in the Ewasm team, right? Hypothetically, what if everything, so once we have Ewasm support on-chain, right? So the left side here is sort of the Ethereum client. I'll go back to this, right? And the right side is the operating system. But if they're both running Ewasm, if they're both capable of running the same apps, the same bytecode, why have any distinction at all, right? Why not just have everything run through the same stack? Now, I mean, there's you're probably all thinking like, that's crazy. Why would you ever want to run, the photo editing software that you're using to make cat images on Ethereum? Like, you wouldn't do that today. That's dumb. You pay a huge price of gas and stuff, right? But bear with me. Let's keep moving. Again, hypothetically, we're taking another step off the deep end here. What if we just kind of like collapse this a bit further and just say, we have this thing. Call it what you want to call it. WebAssembly operating system, called Ethereum OS. That just has native Ewasm support, right? And so things are just running on this Ethereum OS. And what this kind of means, and we're well into the future now. We're at least 5 years into the future, realistically 10 plus years into the future. This is my own kind of forecast / hope for the direction things go. But if you buy that every device is connected, every device becomes a node, right? You have sort of baked in Web3, blockchain, Ethereum support in the operating system. Every device is inherently a node in that network. It's not so hard to kind of envision a world where this could be possible. So we have a bunch of Ethereum nodes that are running the same stack you just saw. So they're running apps, e-apps, whatever you want to call them. Apps that are compiled to Ewasm bytecode, that are running an Ewasm interpreter, that are running on Ethereum OS, that's running on hardware. So I think this is the last slide. So this is kind of the question I want to leave you with. What is an app? Right? We have some super basic computer science questions that we get to ask in a world like this. If all these nodes share state, share the same account data, the same code, and the same state of running apps or dApps or smart contracts, again, whatever you want to call them, then what's an app in the first place, right? Could you envision a world where like the app transcends the hardware, where the app is just this thing that exists simultaneously everywhere and nowhere? It's just part of the state of the network. And you can envision firing up an app on one node, again, if you buy that every device is a node, and maybe freezing it because its computation is deterministic, like it's after some number of steps, and moving it and running it on some other node, right? So this is kind of the pie in the sky vision of the world where I, start something on my phone, and then I get home and I put my phone in my pocket and I open up the same app on my desktop, and it's literally the same app with the same state, and that's possible because these are both devices that share state on some global network, which I'm calling Ethereum, but who knows if this were ever to come to pass, then it might be something else by then. Or another example here, we have an app that's running on one device, and we decide, hey, we need more security, right? We need consensus on a higher number of nodes, or we need more compute power. So again, if an app is this thing that's just out there, and as I said, it's kind of everywhere and nowhere at the same time, could we just crank up a dial and say, hey, instead of running this piece of software on my phone, I want to run it across all the devices in a consortium network at my workplace, or all the nodes in a particular shard if I need like maximum consensus and maximum security. Cool. Thank you for listening. That's, as I said, just this pie in the sky vision. It's an exploration. Love to continue the conversation. Yeah, if you guys have questions now specifically about this, we can take them. Otherwise, let's do a quick break and then do the panel. So yeah, find us on Gitter, as you heard earlier, or on Twitter. Email, actually, I should just remove my email address. Email's terrible. Any questions about this stuff? All right. I think you'll need a break, so we'll see you back here in 5 minutes. Thank you. Oh, is it like?
I can't. Thanks. I don't know.